We are Tesla V2, and we did our project on optical flow for vehicular speed estimation. Joining me today is
Connor McLean.
Hayden Sather.
Bhuvan.
My name is Braden O'Callahan. For our project, we focused on tackling a challenge put forward by Comma AI. This challenge was to predict a car's velocity using only dash cam footage in real time. This challenge was created as a way of finding potential job candidates for Comma AI, and the best performers have an opportunity to earn a position at the company. This is important because traditional speedometers use the rotation speed of the wheels to determine speed. However, this cannot always be trusted. In many circumstances, particularly while the car is sliding, this method of determining speed will report a much lower speed than the car is actually experiencing. In these cases, if machine learning algorithms are responsible for operating the car, it may be difficult for the driving algorithms to make decisions since they don't have accurate speed data. Having the algorithms be able to accurately determine the speed without the use of a speedometer in a similar way that a human could allows for a more educated response to the car sliding. Using a method for calculating speed without the speedometer also means that we're pulling more information from the sensors that we have. And with driving, better awareness of the car and its surroundings is rarely a bad thing. For this challenge, Comma AI provides a 17-minute training video from a dash cam on busy streets and a corresponding text file with the speed of the car for every frame in the video. Comma AI also provided a 10-minute test video without the corresponding speeds. Our model's results on this video will be sent to Comma AI for them to evaluate using the true speed they collected for the video. Unfortunately, we cannot rely on Comma AI getting back to us in time with our evaluated MSE. So we will evaluate the performance of our model by doing a train test split on the training data that they gave us. Next, Bhuvan will talk about our model.
Training data is basically optically generated images, and the outputs are trained on the corresponding speeds. So talking about our model is pretty straightforward. We have a three consecutive layers stacked up with 2D convolution, followed by max pooling for 3 times, and then again followed with flatten, and again 3 consecutive layers of dropout and dense. So we try to mess around with different kinds of combinations of layer sizes and kernel sizes, but at last this seems to work better. So a kernel size of 3 seems to work better, and a max pooling incorporated of 2 elements, and Adam optimizer was used. And for evaluation purpose, we used mean square error for calculating it. This is an actual network. So talking about how does the model make sense of the the images which we generated. So with the help of optically generated images, we can actually get to know how speed is the consecutive frames are getting. Can you go to the next slide? Yeah. So we have an intensity value at one particular coordinate, and that is getting shifted in the next consecutive frame. So based on how fast the car is moving, we can get to know how is the intensity getting changed. So using that data, we will be trading our corresponding speeds. Next, Connor will be talking about the data processing.
Yep, so using this idea of optical flow that Bhuvan talked about, we created a set of images based on the original dashcam footage, but ones that showed the relative motion of pixels between sequential video frames. An example of this is shown in the images on the bottom. The left image is a frame taken from the original dashcam footage, and the one on the right is its equivalent optical flow pattern. These new images were used to train and test our model, and initial test results weren't actually the greatest. Our model produced a mean squared error close to 10, so we decided to start looking into how we could improve our results. One thing we thought that might be happening is that the model was taking predictions based on other objects' optical patterns and speeds, such as things like cars or even the clouds in the sky. So to get around this, we decided to alter the optical flow input images so that they would only take and include data relative to the motion of the car itself. To do this, we used homographic transforms to transform the original image to a top-down view, which only included the road in front of the car. And the images below show how this kind of transform works. Basically, we take one picture and use rotation, translation, and affine transforms to change basically one image view to another perspective. So when we actually applied this to our own data and frames from the dash cam, what we could do was select a region of interest, as seen as on the image on the left, and then use the homographic transform to produce a top-down view of the road, as shown by the red outlined image on the right. Then this image could be combined with its next sequential image to produce an optical flow image. This is what we actually ended up using to train our final model. Now I'll pass it over to Hayden to talk a little bit about the actual training and final results that we achieved.
So we split the provided data into an 80-20 ratio for training and testing. The first 80% of the video, which corresponds to the first 13.6 minutes of the video, was used as training. And the last 20% of the video, which corresponds to the last 3.4 minutes of the video, was used as testing. We chose this ratio because it's standard for the industry, and we chose to use the last 20% of the video for our testing because we wanted our training and testing data to be continuous, and it also made more sense chronologically to use the last bit for testing, even though we could have used the first 20 for training and the last 80 for testing. After we train the model on the 80% split of the training data, we then test our solution on the last 20% of the data that our model has not seen yet. We use all the same image preprocessing that we use for the training of the model, and our output for the model is in a text file, and it has the predicted speeds for each image frame in a file called test.txt. We had incredible results. The official AI website where this challenge was posted had this description on their page. We will evaluate your test.txt using mean squared error. Less than 10 is good, less than 5 is better, and less than 3 is hard. When you ran our algorithm on the 20% test data, we had a mean squared error of 1.77 miles per hour. This is much smaller than the 3 miles per hour MSE that was their best desired MSE range. We sent in our solution to AI and are awaiting their response on the effectiveness of our algorithm trained on their new test video, but we do not know if they will get back to us with our MSE in time because they're the only ones who have the secret ground truth test.txt file. However, since we achieved such a great MSE on our train test split on the training data, we can confidently say that our solution is sufficient for our purposes and is proof that our model works. We can conclude that our model can accurately predict the speed of a vehicle based on just a dashcam image. As more data is used to train our model, it will get more effective, and this solution can be used to improve the effectiveness of a self-driving car by providing more information to the decision-making system, and can possibly even save lives. That's our presentation. Thank you so much for listening.